Okay, we're starting chapter 8 now. Chapter 8 are on what are called confidence intervals. And just like chapter 7 was broken down into one for proportions and one for means, same thing here. There's going to be a section on confidence intervals for proportions and a confidence interval for means. 8.1, we're going to start with a confidence interval for the population proportion. So we're going to do proportions first. Oops, confidence interval, specifically confidence intervals for the population proportion P. Recall that P hat is the sample proportion. P is for the population proportion. P hat being an attempt to estimate an unknown P oftentimes, which is what we're going to be doing, using P hat to estimate or get an idea of where an unknown P is actually is. We're also going to use this section to do the background for all confidence intervals, so this one gets a little bit long, but a lot of the background that we do here just will apply to the confidence interval for means as well. And a lot of background. So a confidence interval. Sometimes abbreviated CI. That's very common in various studies and statistical analyses. Is an interval, which is a range of values, symmetric about the mean. Back when we started to do the things that we will need to do this as z-scores, we said symmetric about the origin, but here it's going to be about the mean. Symmetric about the mean. Which contains the specified probability. So it is related to that problem where you're finding the negative and positive z-score to get that interval. Symmetric about the mean, which contains a certain probability, the specified probability. Confidence interval. That specified probability that we're referring to, which could be any probability, tends to be on the high end, and there's some standard ones, 90% confidence interval, 95%, and we'll do some weird ones like 87%, and just to make sure we know how to do it, even if it's not one of the ones that's commonly used. The specified probability is called the confidence level. Where am I going to put this? A critical value? I can fit it here, I think. A critical value denoted Z alpha over 2, so it's an alpha. Looks like a little fish. Greek symbol alpha. Alpha divided by 2, so it's a subscript that's a half of alpha. Is a z-score with alpha over 2 probabilities to the right. Now a lot of the things we're doing here we've seen before, and I gave you that problem with z with a subscript, and that's what it's referring to, the probability to the right. And all this comes together in a visual picture of what how a confidence interval is going to be broken down. We're going to be using some z-scores and translating it to a different a different normal curve. But let me draw a picture about specifically how the alpha factors into this. It's a little bit weird. You don't really need to tackle with the alpha over 2. You have actual numbers to work with, and it'll be simple. It'll be like those problems that you dealt with where you found the z-scores that trap 70% in the middle. But the background for this is a little bit weird. We're going to be looking at a standard normal curve to start off with. And for a standard normal, the mean is your origin. And just like for those problems that we did, you will be looking for a negative and positive z-score. That's intended to be symmetrical. Yeah, it's okay. Okay. That contains a certain specified probability trapped between them, or contained between it within that interval. That's called the confidence level, that area that I shaded in red. And back then I was just labeling this a negative z and a positive z, and I'd have you find those z-scores. The technical labels for these are, and let me not put it in red. This one is z alpha over 2. This one is negative z alpha over 2. So you will have a negative and positive z-score. You will be using that sort of thing that we did. But the alpha over 2 specifies that this area in the right tail, that's what that subscript represents, and so that is area alpha over 2 to the right of that z-score. It's symmetric, so that means its left tail has alpha over 2. Combined, that makes alpha and the two tails combined, which means your actual confidence level which is a probability in red in the center, is 1 minus alpha. And oftentimes we'll refer to percentages for the confidence level. That's a pretty standard thing to do. So we will need to be able to go back and forth between the decimal form of it and the percent. So I'm going to write, and this is common in books to write times 100%, so that means we would express it as 90% confidence level or 87% confidence level. But that's how the alpha factors into how it's broken down. It really looks confusing that you have alpha over 2, and 1 minus alpha in the middle. But don't worry. In reality, you're going to just have 90% in the middle, 5% on each tail, and then just work with that the way we did. So you won't have to really grapple with why they chose this particular convention for expressing it. I'm not even sure myself. But that's where the alpha 2 comes from. That's why I just want to clarify. You don't really need to deal with it. The interval. Okay. I guess I have a bullet point that's I kind of just said already. But so the interval, negative z alpha over 2 comma z alpha over 2. This interval right here contains the 1 minus alpha confidence level. All right. Mention it now. The margin of error. Something you may have heard before. We will talk about it, and it's literally the same margin of error they refer to in polls and political analyses and election predictions, which is pretty recent for us in this semester. This semester being fall 2020, but I think I'm going to use this video for our next semester, so my references may be 6 months out of date. The margin of error is the radius, which is half the length, not the radius of a circle, but the radius of an interval, which is half the length of the confidence interval. And I'm probably going to get lazy and start writing CI eventually, so I'll note that CI for confidence interval. I haven't done it yet, but I will. Okay, that's a lot of definitions. Let me give you another picture. They're all going to be normal distributions. They're all going to be bell-shaped curves. We're working extensively with that in this section. Oh, my rags are filthy. I gotta clean them. Anyway, I'll draw it a little bit smaller than I would otherwise. I'm running out of room. But for proportions, you're going to survey a bunch of people, theoretically, and get a p hat. You don't know p, you don't know the population proportion of all people that support the death penalty or whatever, but you can take a sample and you can get and calculate the percent of your sample or the proportion of your sample that supports the death penalty, and that'll be your p hat. That's what's called your point estimate. I did use that term. Let me throw it back in here. But rather than just use that as our best guess for the true but unknown p, we're going to create an interval by going out. Oh, I forgot to write it over there. Margin of error. I didn't write my notes. Anyway, sorry, margin of error denoted by capital E in our textbook. Margin of error denoted by E. Some things use an acronym of MOE. That's not something. We're not going to use that. But margin of error, literally that acronym for margin of error. Our book and a lot of books use capital E for the margin of error. Anyway, back to my picture. We're going to go out to the left and right. That margin of error. And so we'll get some boundaries. Here, here. That's going to be p hat minus E as my lower boundary, and p hat plus E as my upper boundary. And within that interval, within those two boundaries, will be whatever confidence level we're going to be doing. So that's going to be how that picture breaks down and relates to the margin of error. We'll be adding and subtracting the margin of error. That's why when you see margin of error, they'll say plus or minus 2.5%. or something to that effect, because you're going to be create an interval by adding and subtracting it. For means, can I fit this here? I'm sure going to try. For means, you want to estimate the population mean, the average height of all adults, humans, or all adult Americans, and it's impractical to get that information, so you generally will take a sample and use that as an estimate. And that sample, it's going to be labeled X bar, the sample mean, the average of your sample. And that is your point estimate that we referred to last time in chapter 7. That's your best guess for the true but unknown mu. But for this section, we're going to not just stick with that point estimate. We're going to create an interval that we are blank % confident in. They use the capital E for margin of error here, even though it's a different context proportion for means. They still use capital E for it. The formula for it will be different though. And so our boundaries for our interval will be X bar minus E and X bar plus E for means. And you'll have an interval and you'll be blank % confident or 90% confident that the true mu is somewhere within there. You can't guarantee 100% it's going to be there. You're just 90% confident or 95% confident or whatever confidence level they specify. And we'll start working with that in a little bit. First, we want to make sure we can do some critical values, get these z-scores. We've done it before, but let's redo it in this context. Let me put my instructions here. I'm going to have you find the critical values for the following confidence levels. To illustrate this, we're going to do three. We're going to do the three common ones, which are 90%, 95%, and 99%. And I mentioned, and I'll mention again, I'm going to give you weird ones like 88% or 96%. The technique that we use here will apply to those as well, and we'll see them coming up in real examples. But for now, I just want to make sure we get down the basic ones that are commonly used repeatedly to the point where some people just memorize the critical values for the three common confidence levels. 90%, let me see if I memorized it, is 1.645, I think. 95% is 1.960, and I don't know 99% off the top of my head, but I can figure it out. But they're so common that sometimes if you look online, they'll just give you that number and not really explain where it's coming from. We are going to figure out how to get it. And we've actually done this before. We've done these problems a few times now, and it came up on your exam. It's just not worded in this way, so it's a different wording, but it's a process we've done. Because what we're trying to do is, we're trying to find a positive z and negative z score, making a symmetric interval around the origin. Specifically, I'm going to use the labels. That's z alpha over 2 now. That's what it's called. You don't need to worry about what that alpha is. I talked about it, but I said don't worry about it. It's beyond what we need to deal with. But we do need to understand that we're looking for those two z scores that contain 90% in the middle. So 0.90. We'll use a decimal form always. And we're going to use inverse norm. Because inverse norm takes areas under the curve, up top, above the axis, and it will get you the corresponding z-scores. So we need to find all the areas, specifically the tails. And I do that by doing the complement rule. 1 minus 0.90 will give me 0.10. 10% is outside of that, so 9% in the middle, 10% on the outside, but that's both tails combined on the outside. So do not forget, you have to divide it by 2. The whole thing needs to total to 100. And for that to happen, you need 90% in the middle, and then equal amounts on each side. That means 5% and 5%. So 1 minus 0.90 divided by 2 will give you 0.05, and don't confuse it with 0.5, and don't confuse it with 0.005. Let me just... 0.5 is 50%. That's half of the total area. That's not something we're going to be dealing with for confidence levels. 5% is going to come up a lot. 0.05 is 5%. It comes up right here. And be aware, we will also deal with 0.005, which is half a percent. This is 5%. This is 0.5%, which is not the same as 0.5, or it's not. That's half a percent, less than 1%. And all of these will come up, so you have to watch that decimal placement carefully. Be careful, please. Okay, anyway, I'm ready to go. I've done this before. I'm going to plug in inverse norm 0.05. It'll give me this z-score, the negative of it, but then once I have that, I'll just drop the negative. So my actual answer, z alpha over 2, will be positive whatever. Where's my calculator? Inverse norm 0.05. Remember that inverse norm takes the area to the left, so when I put in 0.05, it means I'm intending to get the one that has 0.05 to the left. This is the negative side. Doesn't matter as long as you're aware that we want the positive one, so we'll just drop the negative. 1.6448, but I got to round it to 3 places, so that's going to give me negative 1.645. Technically, the critical value is the positive side. We found the wrong side, but it's fine because we know that it's positive 1.645, that's it. And I'm not really concerned about the sign, because when we work with it, we're going to be doing the negative and the positive. We'll be doing plus or minus, so it won't really matter about the sign. I'm not super concerned about that. Anyway, that's your critical value for a 90% confidence interval. It's always a critical value for any confidence interval as long as it's for 90% confidence. Let me continue on. I'm going to 95, then 99. Much quicker though. Okay, 95%. This is a super common one. It's going to be, it has to have more area, so it's the same curve, it's a standard normal curve, so to have more percentage of the area, it needs to be wider. It's going to be a bigger number. So I'm going to draw it a little bit wider to emphasize that. But these are definitely not to scale. This So I'm going to want 95 in the middle, 0.95. Pause it here and work it out if you can, I guess. And then come back and make sure you know that you want to take 1 minus 0.95 divided by 2. And that'll give you not 0.25, watch your decimal, it's 0.025. It's not 25%, it's 2.5%, that's 2.5%. So watch that decimal placement and know that there's 0.025. Still inverse norm. We'll be doing that a lot for these. 1.9599, if I round this to 3 places, I have to bump that 9 up by 1, I have to carry a 1, and that 5 becomes a 6. So this is negative 1.960, but the z alpha over 2 is positive. Again, I don't really care whether you put the negative on there or not, but be aware. Negative 1.960 is there. This is technically the critical value, positive 1.960, but the main thing is you'll be able to get that value. And the signs, again, we'll be using both negative and positive. Last one, 99%, and I'm going to pause it and we'll get into some actual examples. Oh, we'll get to the confidence interval formula. Yeah. 99%. Pause it here. Go ahead and do that. Make sure you can do this. I'm going to draw it smaller. I'm out of room, man. You got the idea. It's going to be wider even more, so it's going to be bigger than 1.960. It's actually going to be 2 point something. That I know. Let me draw it wider. You want 0.99 in the middle. Each tail will therefore have 1 minus 0.99 divided by 2. And that's going to give you 0.5%, because it's going to be 1% cut in half. Decimal form will be 0.005. Again, that's 5%. That's 0.5%. So again, you'll see a bunch of those and you need to not confuse them. Inverse norm, 0.005. You got 2, 5, 7, 5, 8, so that second 5 rounds up to a 6. 2, 5, 7, 6. I'm not going to bother writing the inverse norm because I'm just going to go straight to positive 2.576. And feel free to do that. If you're doing a test, write inverse. Nah, it's fine. You'll be doing a lot more showing of work, and that's something that probably you don't need to bother to put. Okay, I'm going to pause here. So that's that's 3 examples of critical values for the 3 most common types of confidence levels that they do. But you will have to find weird ones like 0.88 or 0.92, and then you'll just have to do this process and get a weird number there and get that z-score. You did it on your exam. Okay, so that was a background that applies to both, sort of. Yeah. But now we're going to actually look into confidence intervals. For the population proportion P. Given a sample proportion P hat, calculated from a sample of n items, or sample size of n items. Alright, calculated from a sample of size n. The blank percent confidence interval, oops. Instead of putting blank, I'm going to actually use the notation, the alpha notation, but again, don't worry about that. You're not going to deal with that. You'll be dealing with 90% or 95%. You don't have to worry about alpha. on the blank percent confidence interval. For the true, and I'm going to write a little bit of extra words here that I won't be always writing. For the true but unknown, usually unknown, population proportion P is given by, and here's the formula, it's on your formula sheet. It's P hat plus or minus Z alpha over 2, that critical value that we've just spent some time figuring out how to find, times the square root of P hat Q hat, which is 1 minus P hat, divided by N. That's your confidence interval formula. The plus or minus means you're going to do two computations. You're going to do minus and plus to get an interval by adding and subtracting. Or I said that wrong. Subtracting and then adding. Doesn't matter what order you do it in, as long as you put the lower one on the left, the upper one on the right. You'll see in a bit. And as a bullet point, my bullet points are going to go up here. When I ask you to explain what it is, and we'll see an example of this, your explanation can be, we are blank percent confident that the true population proportion P is between the lower and upper bound that you get by doing this computation. And the lower bound is P hat minus the Z alpha over 2 times the square root of P hat Q. Remember that, basically that, but with the minus there. That's your lower bound, and P hat plus that same thing. And on your formula sheet, it's not, this is the condensed form where I just put plus or minus to capture both the lower end and upper end. On your formula sheet, it's actually broken down into an interval with this as your lower, this is your upper with a comma and interval notation. So just be aware of that. Sometimes for formula sakes, they split it up. Sometimes they'll write an inequality to capture this idea. You don't have to write this down, but they'll say we are blank percent confident that P is between those. So you do have to distinguish between P hat and P and make sure you know the difference. This is your population proportion, the proportion of all Americans who support Trump, let's say, and you're going to be 95% confident that it's between that percent and that percent. So this is calculated from all sample information, P hats. So you're getting this and this from the information you gather from the survey, and you're confident that the true percentage of Trump supporters is between that bound and that bound. That's the idea. We'll see some concrete examples of some numbers. I also mentioned earlier that the boundaries you get by taking P hat minus E and P hat plus E, which means that within that formula is the formula for the margin of error E. Let me write that as a bullet point. A second bullet point. The margin of error on a confidence interval for the population proportion is everything after the plus or minus, the z's part of it, times the square root P hat Q hat divided by N. So that's your margin of error. It's a z-score times this. This is your standard error that I mentioned that we're not really going to use that term, but that's your, I'll write it in here. No, I don't want the abbreviation because we're not using it. You write the whole thing out. We won't really be using this term too much, but you'll see it in other textbooks, and sometimes if you do go on Khan Academy or something, they might start using that term a lot. We don't in our book, so I'm not going to really use it, but it's a z-score times the standard error. We'll actually look at that more closely and get a feel for what this is actually trying to do. It's not as bad as it looks, and it looks crazy, but really, we got it. Don't worry. But let's do an example right now, a concrete example with some actual numbers. I'm going to pause though. Okay, suppose in a survey of 28 American adults, six believe the moon landing was a hoax. Okay, and we're going to just do the basics of confidence intervals, and then later on we'll do more extensive examples where we kind of get into it a little bit and dig a little deeper. But here I just want you to see the types of problems you'll be asked to do and just get those problems out of the way. So first one, A. Calculate the sample proportion. I'll specify the symbol that we're using for that, or remind you of the symbol that we're using for that, but in theory the question may not mention that symbol. You have to remember sample proportion. The proportion of your sample of 28 that believe the moon landing was a hoax is symbolized by p hat. Calculate the sample proportion p hat that believe the moon landing, I'll just say believe moon landing hoax. I'm going to shorten that phrase for brevity. Okay, so just a basic calculate the sample proportion. And we've done this before. It's p hat. I gave you a symbol as x over n and told you what those mean, but you don't need to know that. You just need to know what you're doing. You're making a fraction out of this sample. The fraction that believe the moon landing was a hoax. So it's out of 28, and how many believe that? 6. And doing a decimal calculator on your calculator and rounding off the 3 places for proportions, which gives us down to the 1/10 of a percent. 6 divided by 28. And I got 2142, so if I round to 3 places for proportions, as we did in previous sections, but I'll mention again, 214. That's 21.4% of our sample believe the moon landing was a hoax. 3 places for proportions will be a standard. Because that'll, again, give you to the 1/10 of a percent, 21.4% if we mentally convert it to a percent. That's it. That's all you want. Leave it as a proportion, so leave it in decimal form. Okay, B, I'm not really going to ask you on an exam situation, but it's more a conceptual question. Given no other information, what is our best guess for the true but unknown proportion of the population, but I'm going to specify of American adults, the proportion of American adults, that's our population of interest. Because they said it here, they don't care about Europeans, and they don't care about kids apparently. They want to know American adults and what they're thinking. The true but unknown proportion of American adults that believe moon landing hoax. So the idea here is we're interested in the proportion of all American adults, all the American adults walking around that you're going to encounter. What proportion of them believe the moon landing was fake? Given no other information, we only have this sample to go by. That's our best guess. So just conceptually, that's our estimate, given no other information. 0.214, and I'll emphasize here, that's can be interpreted as a percent of the American adult population. Okay. I'll circle that though, technically it's 0.214, because it's proportion. And this is our point estimate, and it's called that because it's a single point on a number line. It's a single value, which will be in contrast to an interval, a range of values, which we're going to be building towards now, because this is the whole point of this section, is not to just get an estimate, but to get some range where we're Well, we're going to be doing 90% confident. C is going to ask you to calculate a 90% confidence interval. Calculate a 90% confidence interval for the proportion of American adults who believe the millennium was fake. And I'll, this one time again, emphasize this is the true but unknown. And I'm going to get away from writing that in the future, but I'm kind of emphasizing now that the true proportion of American adults is an unknown thing. We don't know that. All we have is a sample to work with, but we're going to build a confidence interval for the true but unknown proportion. I'll write population proportion. It's implied, but I'll write it anyway. Population proportion of American adults who believe moon landing hoax. Okay. So our best guess is 0.214 for that proportion of all American adults that believe it. It's probably not accurate. It's a very small sample size. It could be way off. It could be a little bit off. But we're going to make a 90% confidence interval and talk about that. So this is our first confidence interval. If you're working on the exam and you encounter the confidence interval, what I would immediately stop and pause and think about is, are we doing a confidence interval for proportions or for means? Are we doing averages of things? We haven't done means yet, but that's the thing you're going to have to decide on, because we're going to be doing two different types of confidence intervals. Anyway, all we got for now is proportions, so that's what we're doing. And I'm going to mention right now my strategy will be to hold off on that whole formula and organize the things that we need for that formula. So what I need is a p hat, a q hat, an n, and a critical value z specific to the confidence level. So my work for C is going to be up here. Let me write that one I just did. So continuing this up here, I want to figure out p hat, I want to figure out q hat, I want to figure out n, no, I'm going to put n over here. And I want to get that z score, what's called the critical value. Okay, our p hat is our sample proportion, 0.214, we did it earlier. That's going to be used in our computations. Q is 1 minus that. Whenever you have a q hat and a p hat, they're related by their complements. It's a proportion that don't believe the moon landing is a hoax, but they just use it for convenience rather than writing 1 minus p hat in your formulas. I will mention that some of them do, by the way. Let me just mention this real quick, because in case you take another course and you, Psych 5 especially, instead of q hat, they literally write 1 minus p hat. It's equivalent. That's equivalent to that. But they don't incorporate a q hat into the formula. They just put a 1 minus p hat there. But that's what we are calling q hat, which is point. I'm gonna do this. It's late. I'll mess it up. 786. The n, I erased it, but it was 6 out of 28 American adults, and make sure you don't use a 6 as your n. It's the full sample, the ones that believe the moon landing was a hoax and the ones that don't. All 28, was it? I erased it, but yeah, it's 28 that were surveyed, so that's your sample size, that's n. Your z, if you don't know it off the top of your head and you don't remember what we did 10 minutes ago, you have to do a fresh picture and find the z-scores. You don't need to label all this detail with the n01, but you're definitely going through that process of getting a z and a negative z. You can put the alpha root 2 if you want, because that's what we're finding, but what do we want in the middle? What confidence level? 90% in the middle. That means I'm not going to show the computations, but 1 minus that divided by 2 will be 0.05. I'll do inverse norm 0.05, drop the negative, and then I'll remember, or I'll recognize that it's a z alpha over 2, that first example we did, 1.645. That's our critical value that we need. If you knew it, or if you knew where to find it in your notes, just use it. But again, be aware, I'm going to give you weird ones that you're going to have to definitely do fresh. 88% is not a really commonly known one. 96% is not a commonly known one. But if it's a well-known one and you remember it, just use it. 1.645. Alright, we're ready to put it all together and do our first computation, but let me fix this and put it back the way we're used to seeing it. Alright, so let me write it down. Let me copy it down. P hat plus or minus z alpha over 2 square root p hat q hat over n. And we'll make sure we know how to compute that square root with a fraction or the square root. I think we've done it before. We've done similar things, yeah. 0.214 plus or minus 1.645 times the square root of 0.214, 0.786 q hat divided by 28. Just plug in the things that we need, and it does help you to have it organized and ready to go ahead of time. P hat plus or minus the z times the square root of p hat q hat divided by n, all that under the square root, and let's make sure we can compute it. What I'm going to do is I'm going to compute the margin of error first, and recall the margin of error is everything after that plus or minus. So I'm going to start, I'm going to show you, I don't have to erase, but I'll write what I'm writing, or typing in. I'm going to put 1645 times, hit the square root button. So I'm including that z, that 1.645, and then times the square root, and I'll get a number, and that'll be plus or minus that number. So what I'm doing is a margin of error. Square root. I'm going to mention that if you have the roof, just make sure everything's under the roof. And don't bother with parentheses. Again, when I write the parentheses on the board like this, there's no need for me to put that into the calculator. That's me so you can see the two separate numbers that need to be multiplied. I'll make it readable, but the calculator doesn't need it. The calculator can just take a string of values with a multiplication symbol between them. So I'm just going to put under my square root 214 times 0.786, that's a multiplication symbol, which comes up as a star, as I'm sure you have seen. Multiplied by 0.786 divided by, which will show up as a slash, 28. And make sure the roof is all over all of that. Go ahead and do it. Make sure you do this, because again, this is one of those things where if you just kind of skip out on it and then think you can do it later, you may not be able to. If you have the older versions, the TI-83s, you don't get the roof extending. You get this the square root with the open parentheses. And again, if you start putting these little parentheses within these numbers, it's going to mess you up possibly. So I wouldn't bother. I would just put 0.214 times. You don't want to put a parentheses there because that closes off the square root, and that can mess you up. You don't want to close off the square root. You want to include the 786 and the divide by 28, and then close off that square root. So just one set of parentheses for the square root. Don't bother with the little parentheses separating numbers. Go ahead and do this. And this will be also a proportion, and so you're going to round it off to 3 places as well. I got 0.127 rounds down, so 127. I'm going to erase this, so this is me just showing you what to type in on your calculator. You can leave it in your notes if it was helpful, but I don't want it cluttering up my notes. I would just, in this case, I'll just go straight to that, figure out what it is, get 0.127. I admit I'm being inconsistent with putting a 0 in front because it doesn't matter, but make sure if you don't put the decimal clear. I feel like I'm actually being sloppy here, so go backtrack and fill them in. Okay, anyway, that's where we're at. We're not done. I want to find the two boundaries, my lower bound and upper bound. So I'm just going to do 214 plus 0.127 and 214 minus 127. But here's the thing. I'm going to make an interval out of this, and the interval is going to be interval notation with brackets and parentheses or whatever, with your lower bound there and your upper bound there. For confidence intervals and our intervals that we deal with in this class, it's parentheses, parentheses, but so we don't deal with the bracket part, but it's the same interval notation standard, but I just did 214 plus plus 0.127, and I got 341. Do not put that here, that's a wrong side. Even though I did the plus first, the plus is the upper bound. So that's wrong. The 314 is here. So I don't care what order you do it in on your calculator, but make sure you put it in the correct order on your paper, your final answer for your confidence interval. It's the lower bound here, the one you get by minusing. And the upper bound next that you get by adding. And that's it. That's our confidence interval. And sometimes they write P like that. You don't need to. This is your answer right here. When you see that symbol, it does come up. It's used in our book. And I sometimes throw it in answers. That symbol right there, it's like an E. It means it's contained in or is a member of. It's set notation, but that is contained in. That's not that important. You don't need to use it. But P is contained in that interval. So we're pretty sure that P is between these two values. How sure are we? We're 90% sure. That's what that confidence level is. Okay, but let's elaborate on that explanation. With a question that definitely is going to be on your exam and your homework. That's the end of, that's the answer for C, right? Our confidence interval. So that's our first confidence interval. What was that? C? D? D is next. I'll explain. What this interval represents. And so we're going to explain in words that concept, so I'm going to make sure we understand it. Okay, so that's our question. Explain what that confidence interval represents. And here's our explanation. We are blank % confident. You can kind of follow this template every time they ask you to explain a confidence interval because they all represent rough, it's the same idea. We are blank % confident that I'm not going to write the usual, the true but unknown, that's implied. I'm just going to write the proportion. So I'm going to start condensing things down and not being as wordy about it. We are blank % confident that the proportion of American adults, that's implied to be the proportion of all American adults, that believe the moon landing hoax is between blank % and blank %. So since I'm thinking of as an explanation of it to like a lay person, to your friend that hasn't taken stats yet, we're going to mentally convert everything to percent so it's easier for the typical person to understand. But you can leave it in proportions in decimal form, but I do want to get an idea of what we just found. How confident are we? Whatever confidence level we did. I erased it, but you can, that's 90, sorry. That's 90 and I wrote it so it looks like 99, but no, that's 90. We are 90% confident because we computed a 90% confidence interval. That the true proportion of American adults that believe the moon landing was a hoax, which is denoted by P, is contained in, that's what this notation represents, an interval that's bounded by this proportion and that proportion, but if I convert to percent, that's not 87%, that is 8.7% and 31.4%. So that's a pretty wide range of values, and we're 90% sure it's somewhere in there. It could be low like 9%, it could be high like 30%. Our best guess was 21.4%, but we're 90% sure it's within there. But the reason it's why it's such a wide range is because 28 people is not a whole lot to sample. If you want accurate information, you survey hundreds or thousands of people as they do for a presidential election. And we'll get to that. We'll do an example where we talk about more realistic surveys and more realistic sample sizes. But I just wanted to get a feel for the basics of it. I'm not done. I got one more question. What is the margin of error? On our CI, and I am getting lazy, so I'm going to abbreviate the term confidence interval by CI. Okay, and it's not some computation we have to do now because we already did it. You did it. I oftentimes ask this after the fact, after you've gotten your confidence interval, and I want you to go back and figure out which part of it that we did is our margin of error. And I'll remind you that it was everything after the plus or minus. It's p hat, or point estimate, plus or minus a margin of error. You don't have to write this down, but I'll remind you that the picture I drew earlier, p hat, and then you add and subtract the margin of error, and you get your boundaries here and here. So this whole thing is our margin of error, and it came out to 0.127. So it's already on the board, we just have to know where to grab it from. I'll write the capital E to remind you of the symbol. You don't need to, you can just give me the answer, 0.127. And that means our margin of error is 12.7%. It's a very large margin of error, which is why our confidence interval is so wide. If we want to reduce that, we increase the sample size, that margin of error gets smaller, this interval narrows, and we get a better estimate, or we get more confidence and a narrower range of values, and that's how we know, on November 1st that Biden's probably going to win, or whatever we're trying to predict via surveys and polls. Okay, I'm going to pause here, but we have more examples to do to get a feel for this and drill a little bit deeper. Okay, our next example, we're going to look at a hypothetical bag, a large bag. Of M&Ms containing an unknown proportion of black M&Ms. And so this example I use a lot because I did have a couple of labs and a couple of illustrations where I had actual bags of white and black M&Ms, which you can get at a specialty candy shop. They do have them. People would touch the bag and pull some out, and we'd do some simulations, but then you'd have a bag of M&Ms that everybody touched, and I definitely don't want to do that nowadays. But it is a pure form rather than these phone surveys and asking whether they support the president or not, because you don't have to worry about not getting a representative sample, too many women overrepresented because you're doing landlines during business hours, the kinds of things that we talked about in chapter 1 with regards to sampling and the difficulties of getting a random sample or a representative sample and instead getting a bias sample. You don't have to really worry about that with a inanimate bag of M&Ms. So this is the purest form of what we're trying to do, is estimate an unknown proportion of black M&Ms in a bag, not by counting up all the M&Ms in the bag, but by simply taking a sample of them and getting some probabilities and confidence levels based on, in this case, we're going to do a sample of 30 black M&Ms. Suppose a random sample of 30 are selected and 18 are black. Okay, we're ready to start with our second confidence interval. And we're going to go straight to it. We won't have any questions leading up to it. We'll just go straight to calculate an 86%. Not a nice one, not a common one. So we'll have to do a critical value, a z-score fresh, probably. Unless you know the critical value for 86% confidence. I'm going to abbreviate CI for the proportion of black M&Ms in the bag. Okay. For your formula, again, think about whether they're asking about a confidence interval for proportions, percentages of things, or averages, means of things. It's proportions of black M&Ms. We haven't done the means one yet, but it is a question you'll have to keep coming back to once we get through this whole chapter and you start having the problems mixed together in an exam type situation. Okay, p-hat, we didn't compute ahead of time, so we got to do it fresh. It's 18 out of 30. I believe that's 60%, but I'll double check it. I don't want to make any errors. Okay, 0.6. All right, 0.60 to emphasize it's 60%, but in my computations I'll probably go back to 0.6. Yeah, so just be aware of that. We do mentally go back and forth between percent and proportions. My Q is 1 myset. I'm running my calculator for that, which is 0.40. My N, make sure you don't think it's 18. It's not just the black, it's all the M&Ms in our sample, which is the full 30. So be careful about which number you're grabbing for your N. It's your entire sample, whether or not they support the president, or whatever it is. And my Z, it's, as I mentioned, it's not one of the known ones, so let me draw a fresh thing here. Not as much detail as I used to do because I'm going to speed it along a little bit, but I want 86% in the middle. And I'm going to do 1 minus 0.86, type, divided by 2, and that's going to give me 0.07. There's 7% in each tail. Go back if you forgot how to do that. We've done it several times now. But I need that Z, so I'm going to do inverse norm. 0.07. I got negative 1.47, I got to round it up, so 1.476. And my Z is the positive of that. But again, we're going to be doing plus or minus anyway. So it doesn't matter which one we actually use. 1.476 is what I'm using. And I'm ready to go with this. For notes purposes, I tend to rewrite the actual formula down first and then fill in the values. You don't have to keep doing that in your notes or on the exam. But definitely like sort out your things ahead of time and definitely show me what you're going to be using in here. And I would compute, as before, the Z times that as a separate thing and then add and subtract it. For one, that means you get the margin of error as a separate thing that you can then give as an answer if I ask for it later. Okay, my Z is 1.476, square root 0.60, 0.40 divided by 30. Alright, let me do this real quick. I'm going to do 1.476 times the square root of, etc., etc. I got 0.132. So I have a margin of error of 13.2%, and that's centered around 60% our point estimate. And I'll get my confidence interval right now. My lower that I get by subtracting, I got 468. My upper that I get by adding is 732, and therefore we're 86% confident that the true proportion of black M&Ms in the bag is between 46.8% and 73.2%. Okay, part B. Do I want to draw my picture now? Now I'll summarize it later. Let's just do the two confidence intervals. B. Calculate a 92% CI. Based on the same sample, I just want a different confidence level. CI for the proportion of, and I'm not writing the whole thing of the true but unknown proportion, but that's what it is. It's a true unknown proportion of black M&Ms in the bag. I'm just going to start shortening my phrasing to calculate a CI for the proportion of black M&Ms in the bag. Okay, I made this one specifically so you can think about what you can reuse and what you have to do differently, what's going to change here. I'm still going to list everything out, but if it's the same as the last time, I'm just going to grab it from that side. So think about what remains the same and what's changing amongst all of these. It's good to think through as you get into doing these problems. P hat, Q hat, are they going to be the same? If they're referring to the same sample, yes. If they give you a new sample with different data, you got to redo it. But we're still using the same sample, which has a P hat of 0.60. Q hat is there for 0.40. My sample size is still that same 30, because I'm still working with the same sample data. The confidence level changing changes that picture, therefore it's a different Z. So that's what's different here. I'm going to draw a very crude picture. What do I want? 92 in the middle? Okay, I'm not writing all the details. I don't clutter up your picture, your notes with things that we've done many times, but I'm doing 1 minus 0.92 divided by 2, which would be 0.04 in each tail. If you are struggling with that, write up the extra detail, but it's 0.92, 1 minus 0.92 divided by 2, and the same thing on the other side, so 0.04, 0.04, 92 in the middle. 175, and I have to round it up to 1. Okay, I'm out of room, so let me just start recycling some space over here. Going over here. I'm not going to copy it down, I'm just going to go straight to plugging things in. 60 plus or minus 1.751 square root 0.60, 0.40 divided by 30. Different margin of error. And that margin of error is 157. 157? Yeah. 15.7% is my margin of error. My point estimate is 0.60. And from that I'll get a confidence interval that I am 92% confident in. Oops. 443. And 757. 0.443 and 0.757, meaning I'm 92% confident that it's between 44.3% and 75.7%. Your explanation would be the same format with just different boundaries and different confidence level, but you could frame it with the exact same wording anytime I ask you for an explanation. Is that right? 468, 3732, 443, perfect. Okay, let me summarize this and use some pictures to flesh out what this is doing. Because I do want you to understand sort of let's see. So what I'm going to do is I'm going to draw two normal curves, sort of aligned. And so the one on the bottom is going to be the probabilities associated with our actual data. 0.60 is our point estimate. This is normal at centered at 0.60, and my standard error, or the standard deviation of this, is whatever I get when I do 60 times 40 times 30. I actually computed it already. It's 0.089. But that's my standard error right there, which is 0.089. Again, we're not using that term, and you're not going to have to do this. This is just me explaining so you kind of understand what's happening. Okay, and I want to, from here, I want to go out to left and right to get a percentage, not that amount, but I want to do a, sort of, I don't know how far I want to go out to left and right, but I definitely want this to be such that I get a cutoff there and a cutoff there that contains, and I'm talking about my first example, my 86%. So this is my 80, let me write down here. That's not that one, that's notes from before. I'm doing something fresh. This is referring to my 86% CI. I want to have a cutoff there and a cutoff there for proportions of black M&Ms so that I have 0.86 in the middle. And this is a normal distribution with that mean 60, my point estimate, and my standard deviation being based on that. That's one of those, one of those, one of those. My borders won't be on nice standard deviation tick marks though. Where are they going to be? Well, that's where I'm kind of working from here first. So this is doing this thing where we translate region, but this one's backwards from the standard, from the standard normal to arbitrary distribution. And what I found earlier via inverse norm was that z-scores of 1.476 and negative 1.476 gives me an area that is exactly or approximately 0.86. So those are the z-scores that trap it. And therefore I want to just go out 1.476 of these. So I'm just going to go out to the left and right this amount and this amount, which I'm getting by this. 1.476 times those standard deviations. That plus that is 1.476, so 1 and 0.476 there. And that ended up being 132, my margin of error. And I got boundaries of 0.468 and 0.732. So that's what it's doing. It's taking these z-scores, which has that specific percentage inside of it, and using those z-scores, and just like when we did percentiles in 6.3, going from there and getting those marks that correspond to the 1.476 and negative 1.476. So that's what we're doing, and a similar picture would be for the other 92%, but I'm not going to bother to draw it and waste your time, but that's the idea, using z-scores and then translating it to the distribution that's based on, that's centered at our sample data. Okay, I'm going to pause there, and that was again the hypothetical bag of M&Ms, which is not a realistic scenario, but we now are going to talk about how this applies to real life. Okay, a realistic scenario in which you've seen confidence intervals, and you've seen them. They may not have identified it as a confidence interval from a stats class, but it is what they do when they do things like predicting elections or estimating presidential approval or things like that. So suppose in a Pew survey of 1,525 registered voters, (661) approved of the job the president was doing. And I'm going to shorten that by just saying approved of the president. And I think that's real data, but I'm not going to tell you what era it's from, what presidency. I don't want to name and shame anybody, because I think this one's low. Yeah. Okay, anyway. We're just going to go straight to calculating a 95% confidence interval. For the true but unknown, and I'm not going to write it, the true proportion, I'm not going to write that, but it's the true but unknown, I'm just going to say the proportion of voters who approve of the president. Okay, so we're starting off from scratch. We have the data, 15, 25, and 661. Okay, so we're doing your confidence interval for proportions. I need my p-hat, and it's just a percentage, that, but in decimal form, of the sample that supported the president. 661 over 1525. Let me compute that. Oh, I got it. 0.433 when you're on to 3 places, so 43.3% approval. It's not good. And we need Q hat is 1 minus that. My N is, make sure you're grabbing the correct N. I do get a lot of people using 661, but that's just the ones that are approved. N is the total sample size, which is all the registered voters that were in the sample, the ones that approved and the ones that didn't. So don't exclude anybody. 1525 make up your N, your sample size. Sorry, let me go back and do that. 1 minus 0.433 is 0.567. And then our Z we need. I'm doing this in weird order. And you got to look at your confidence level for this, 95%. And if you're doing it fresh and you've never done one before, or you forgot what's the critical values for 95% confidence interval for proportions, you have to do the whole thing where you got to figure out 95%. That means 0.025 in each tail, because you do 1 minus that divided by 2. I'm not going to keep going over that, but so inverse norm 0.025, and you get something that by now should be fairly familiar. 1.960. Let's put it all together. I'm going to do it right here, I guess. Okay. P hat plus or minus 1.960 square root 0.433 0.567 divided by the square root of 1525. As usual, margin of error first. And I got 0.0248. I'm going to round it to 3 places, as usual for proportions, so it's going to be 0.025. That's 2.5% margin of error. .433. Okay. And 0.025, so we're going to add and subtract that. Plus 0.025. Okay, and I got 0.408 and 0.458. And that's it. 408, 458. Yep, we're good. A couple of follow-up questions as usual. First one being, what's the margin of error? I just literally said it, but on the CI, the one we just did, and margin of error is the thing you just computed after the plus or minus the 0.025, as I said. So your margin of error is, I'll use capital E. You don't have to put the E again, but I like to put it to remind you of the symbols that we're using. 0.025, 2.5% is a margin of error. Okay, now I'm going to do that explanation one more time, explain what this interval represents, and then do a couple more follow-up questions to illustrate some new things about it. Explain what this interval represents. And the template you can follow again, we are blank % confident. That the true proportion of voters who support the president or who approve of the president, I'm just going to put the true approval. Sometimes they call it approval rating. That's more a political, shorthand for that. But I'm just getting tired of writing, to be honest with you. I need room though. Is between blank % and blank %. And I'm going to go, you could use a proportions form, but since we're explaining, I'm going to pretend we're explaining to somebody who's never taken stats and who isn't really familiar with, percent and proportions, or they're not that good with it. So I'll convert it to layman terms. How confident are we? Depends what kind of confidence level we used. 95% in this case. We are 95% confident that the true proportion of voters who approve of the president, also called the approval rating or approval, is between 40.8% and 45.8%. So we're confident that it hasn't cracked 50%, far from it, which is never good for a president, but maybe they'll turn it around in the next week. All right, anyway, I got more follow-up questions for this. So this is probably an actual survey. Pew is a polling agency that does, they do all kinds of things, but every day they'll present presidential approval, their estimate for it. They'll also present it, they will give it in a different form. So, let me right here. The media reports these all the time, literally every day. The media will report this exact result that we got as 43.3% approval, with a margin of error of plus or minus 2.5%. So they won't construct it for you and get the boundaries of the interval, but they give you the information that you would need to do that. They give you their point estimate, and they give you the margin of error, usually in percent forms, and they write plus or minus. Some contexts like this. And sometimes they even specify with 95% confidence, because it's 95%. They don't always specify that, because I think that would throw a lot of viewers off because they're not familiar with confidence intervals. But by default, anytime you see a report like this in the media, it's 95% confidence intervals. They default to 95%. And that means for part D, I'm going to write part D and E together. What percent of 95% confidence intervals would we expect to contain the true proportion? We'll talk about this. It's a single answer, no computation to be done, but I'm going to put problem E up as well, question E, which is related. What percent of 95% CIs would we expect to not contain the true proportion? And this doesn't only apply to the last problem, this particular CI that we've been dealing with. This applies to any 95% confidence interval. So let's talk about this. So the idea is, going back to this one, we're 95% confident that the true presidential approval is between 40.8% and 45.8%. So we're 95% sure that the true value lands within there. Now we could be wrong. Sometimes they're wrong. Sometimes, like I've been saying, sometimes they predict Hillary's going to win the election, and then you wake up the next morning and Donald Trump's the president. So they can be wrong, but not that many should be wrong if they've done things correctly and got representative samples, which they struggle with sometimes. So sometimes they have some issues. But if everything's pure and they get a representative sample and all the math is valid, then we expect 95% of them to be true, because we're 95% confident that it would be between here. So if multiple polling agencies are doing these, each polling agency is 95% confident, but some of them will be wrong. Specifically, 5% of them, in theory, will be wrong. 95% of them will be correct, because we are 95%. They are all 95% confident in each of their own confidence intervals. Okay, so that's the idea. And if it's a different confidence level, like 90% confidence level, 90% of them should contain it, 10% will miss it. And we're going to talk a little bit more about this in the next part of this. I got more to do. Okay, sort of a follow-up to that. suppose, so Pew is one polling agency that's very popular or well known. Gallup is another one. CNN, the news network, does their own sometimes. So suppose Gallup and CNN conduct their own surveys. Of presidential approval, meaning the proportion of registered voters who approve of the job the president is doing. Gallup reports an approval rating of 47.6% with a margin of error of 3%. So they'll do their own surveys, get a different sample of voters, and therefore their point estimates will be different because it's random to some extent. It should be roughly close to each other and roughly close to the true value, the true but unknown value. But we're gonna look at all three of these. So Gallup reports that. CNN reported .8% plus or minus, so they've written it differently, they're presenting their work differently, but same idea. They're saying 41.8% plus or minus 2.5% approval. And so they all have different confidence intervals, and 95%, they're all each 95% confident theirs will contain it. Some of them might be wrong. And let's talk about this. Suppose the actual the true proportion of voters that approve of the president, I'm going to shorten it, the true proportion that approve of the president was 44%. Which intervals contained the true percentage? Which means which of them were correct and which were wrong. Which of the CIs contain the true proportion? Okay, well, one thing I'm going to do is I'm going to construct all the confidence intervals. I didn't really put it in the problem, but I meant to include Pew in this. So of the three, I didn't write Pew in here because that's the one we did. So let me write that first. Pew. What do we got? 408, comma, 458. Okay. Now the question is, before we get to the others, the true value was 44%. Where'd it go? And so the question is, did Pew get it right? Meaning, was this true value within their lower and upper boundaries? Is 44% between 40.8% and 45.8%? On your number line, and I'm going to draw a more detailed one later, but let me just sort of visualize it. We got 40.8%. 45.8%, and where's 44%? So Pew is 95% confident that the true value is somewhere in here, and now that we've found out the true value is 44, yep, that is in there. So theirs does contain it. And so I'm going to write that shorthand notation, mathematical notation, as contained in that symbol that I've used before, just to get the idea that 44% is within that interval. So that's what I'll use. And if it's not, I'll just use not is not contained in. So just that with a slash through it. That's a real symbol. Okay, but we're going to do all three and see which of the other two were correct and which were wrong. And I promise you one of them is wrong by design with made-up data. Don't worry about that. So I have to reconstruct these. And I got to do the work somewhere else. I'm going to put Gallup and CNN right below it, and we can see in one area which ones did contain it and which ones didn't. But I got to do some side work because I got to construct their confidence intervals. So Gallup, they have I'm going to do it over here. They have a point estimate of 0.476. And their margin of error is 3%, so I'm going to convert it to a decimal. Make sure you don't use 0.3, it's 0.03. And that's how I'm going to construct it. So basically, all of the work is done for you. So when I give problems like this on the homework or the exam sometimes, people get really stressed out and are confused on what to do. They don't know what to do, and they don't know what the z is, or they don't know n. You don't have to know any of that if they've already computed the margin of error and they've given you the point estimate, because again, we are generally, when we have to work out and crunch all the numbers ourselves, we're using that formula. But recall that this whole thing is just the margin of error. So if you have that computed, if they did the work for you of computing the margin of error, and we've been calling it E, all you have to do is literally take p hat and add and subtract E. You take your point estimate, you add and subtract E, and get your boundaries. And that's what we're doing here. They've done all the work other than that last step of adding and subtracting. All right, let me do it with my calculator, which is disappeared again. God damn it. 0.476 minus 0.03. 0.476 plus 0.03. Okay, sorry, this is all just side work and just half-assed explanation. But I need this room to put Gallup's result. And see if mu is contained in there. So that would be a question, a lot of follow-up questions will ask you, is the true value contained in there? And I'll give you a hypothetical, suppose this is the true value. Is 44 within there? I'm going to erase this, but that's just our computations. That's our result. We got 44.6%, 50.6%, and where is 44% exactly? That's 44.0%. Where does that land? That's short of this. 44 is right there, and you got 0.441, 0.442, 0.443, 0.444, 0.445, and 0.446. So it is outside of that interval, meaning that Gallup got it wrong. They missed it. Not because they did anything wrong, it's just that their sample happened to have a lot of presidential haters, a disproportionate number of them. So yeah, just by sheer coincidence, they were one of the 5% that gets it wrong. I'm going to put that in red to highlight it. No particular reason other than to make sure we can see that cross and know that that's the one that got it wrong. Well, we haven't decided whether CNN got it right or wrong yet. CNN, they presented it a little bit differently, but it's the same idea. They give us a point estimate. We need to convert it to decimal. They put plus or minus, but that's based on the way they wrote it. That's implied to be the margin of error, 0.025. And you'll notice this one had 2.5%, this one had 3%, that had 2.5%. That's kind of the standard that they go for. They like it to be 3% or even better, 2.5%, so they can get a really narrow range and pinpoint how the president is doing with the with the voters. So, and to get that, you need a large sample size, much larger than we've been doing. Other than the last example, 1525, that's about what you need, about 1500 to get this margin of error. And in 8.2, which we're almost there because I'm almost done with this, you're going to learn about how to get that n, how to figure out what the n is, how to figure out the sample size you need, how big of a sample size to get a margin of error to be that small. And it's about 1500, but you'll learn how to get that. Oh, I'm going to do this. I'm getting distracted. 418. Minus 0.025 plus 0.025. 393. I'm going to just write it here. And 0.443. And that is CNN. put a symbol there. Is it contained in there? Think about that. Mostly on this side, which is it? Is that below that or above it? It's below it. You have 443 here, and 44 exactly is just barely inside because you got 0.44, 0.441, 0.442, 0.443. So yeah, it is in there, barely. But that doesn't matter. That counts as getting it correct. So they'll all gang up against Gallup and mock them for getting it wrong, even though Gallup did nothing wrong. They do. They kind of call each other out or throw shade. A lot of times unjustifiably. Okay, I'm not done yet. What I want to show you is something they often do when you have many surveys trying to predict an election. The election that just happened or is coming up, depending when you're watching this. There's literally 20, 30 polling agencies that are trying to predict what's going to happen in the next election. And so you get a lot of these confidence intervals, not presented in this way, presented in the way that it was here, but you could reconstruct it. And you could basically compare them visually. So that's what I'm going to do here. Talk about a visual comparison of stacking these, showing them on a number line. So I've been showing you half-assed number lines. Let me do a more accurate one with 0.35 there. I'm going to go to 50. Okay. 0.40 there, 35%, 40%, 45%, 50%, and then a bit past there. Okay. So these are the percent that approve. Now, I should have wrote it. What I'm going to show you is a point estimate of each. Pew had a point estimate of, I forgot what it was, 433. So I'm going to do, I'm going to do Pew. 433 is about here. And then they had a margin of error of 0.025, and they had this upper bound and lower bound. So what they do is they imagine adding, this is their p hat. I'm going to erase this in a bit. That's 0.433, about there. And then we add and subtract the margin of error, which is 2.5%, which gave us that boundary and that boundary. So it goes out to 458, I want to say about there. And to 408, which I'm going to say is about there. And so this is how they represent confidence intervals sometimes, especially when they want to compare with other confidence intervals from other polling organizations. They show a visual image of the point estimate, the center of the interval, and then they show the margin of error judged by just band going out to the left and right. So that's Pew. Next, Gallup had a point estimate of 0.476. 0.476, I want to say, is about there. And they had a margin of error that was slightly bigger than the rest, 3%, I believe, 3%, right? So they end up going out to 506, about there, 506, 446, about here. And that is right there, Gallup. And then the last one, CNN, they had a point estimate of, where's CNN? 418. This is about here. So their point estimate sometimes is highlighted by an actual point, but then they want to show how wide the confidence interval is, where it ranges from the lower and upper bound. And so ours, CNN goes from 393, I'm going to say it's about here, 393, to 443, let's see about there. Okay, and these should be symmetrical. That's your margin of error for CNN, that's your margin for Gallup, a little bit bigger, that's your margin for Pew, that's 2.5% as well, and that's CNN. And so you can see, Gallup had the highest prediction just by randomness, CNN had the lowest, the point estimates are all over the place, but they're all roughly around the 40 to 45% range, so they're kind of pinpointing where it is. You're definitely not going to get an 80% approval rating based on what, based on this data. It doesn't look like it's anywhere, maybe a little bit above 50%. Gallup says it could be 50%, but the rest are saying, nah, he didn't crack, he or she didn't crack 50% approval. Anyway, On top of this, after the results of the election or something, where you actually get the value like we did, 44%, we said hypothetically, we could throw that on here. 44% is right here. And I gotta kind of do this in a weird way because I gotta make sure I get, that one barely had it. Oh, hold on. 4, 3, 3. Oh, this is not that good of a drawing. But based on this 44, that's your actual P, your population proportion of all voters who approved the president. It was 4-4. And you can see visually, although I gotta adjust it a little bit, CNN barely had it, as we said. So it is within CNN, so you can visually see that. Barely though, we talked about that. Gallup missed it entirely. I'm not going to say entirely, but Gallup missed it. Gallup called it wrong. Gallup said they're 95% sure it's going to be here, but no, it was outside of that, so Gallup was wrong. And Pew had it and had the best, closest point estimate of them all, but again, this is all just based on the randomness of it. They can't really help it when they're wrong sometimes. 5% of the time, when they do 95% confidence intervals, they'll be wrong and they'll miss it. Okay, that's it for 8.1. 8.2, we're going to talk about sample sizes in the N and how they can get the margin of error to be 3% or 2.5%.